Thank you very much for the invitation and for the organization of this nice one-word combinatorics on words seminar. So today I will talk about combinatorics on words for Markov numbers. And this is a joint work with Christophe Reutenauer. So I am working at the Llama. This is the old logo of my lab, but I really like this picture. And I work also at the CNRS. Alors, so it's a really long story. In fact, it's a problem that has more than 100 years. And this is a really nice book of Martin Egner about Markov's theorem and 100 years of the uniqueness conjecture. I really like this book because it's a book with number theory, hyperbolic geometry, perfect matching, tiling, and of course, combinatorics on words. So it's a really nice book. And you have also this, oh, sorry, I have some trouble. This new book, quite new book of Christophe Reutenauer about the problem, from crystal words to Markov numbers. Okay. So this is the outline of my talk. So in the first part, I will speak about number theory. So approximations of real numbers. And then we will go to a Diophantine equation in order to describe the Markov numbers. And then we will have a more theoretical computer science formulation with a tree of Markov triples. And then we'll go deeply on combinatorics on words. Okay, let's go. So first of all, it's a long story. It's an approximation of real numbers. So alpha is a real number. And if you want to approximate the real number by a fraction, p over q, you can calculate the distance from alpha to p over q. And by Dirichlet theorem, this is in absolute value less than 1 over q times n. So less or equal to 1 over q square. So you can go, you have this approximation and you have p over q, and you use, in fact, as a denominator q square. So it's interesting to have such kind of approximation. And if your alpha is irrational, then you have infinitely many rational with distance less than 1 over q square. So this is a key result, in fact. And of course, in number theory, you can define a complex number alpha, and it is called algebraic of degree d if alpha is the root of a polynomial with integer coefficients of degree d. And d is the smallest degree for which such a polynomial exists. So square root of 2 is algebraic, of course, of degree 2, because we have the solution of x squared minus 2 equals 0. Okay. And we are able to define transcendental numbers if there is no such polynomials for any degree. Then alpha is called transcendental. And this is the first transcendental number. You define it as the sum of n equal 1 to infinity of 1 over 10 to the power n factorial. So it means that you put a 1 in factorial position. So in position 1, 2, 6, and so on. And this is the transcendent number. You have E and P and many more, of course. Okay. So if you take alpha, which is irrational and also algebraic of degree d, then you can approximate alpha by a p over q, but we are not so close to alpha, where the distance is greater than c over q to the power d, so the algebraic degree. So it's a really nice link between rational approximation and degree of algebraic numbers. And if we are too close from an irrational, a real number, then we are sure that this real is transcendental. So if you have infinitely many fraction p over q, such that alpha minus p over q in absolute value is less than 1 over q to the power 2 plus epsilon, so we are really close to alpha, then alpha is transcendental. Okay, this is interesting because here we have q to the power 2 plus epsilon. So it's difficult to improve the exponent 2. And so we will try to look at the distance between alpha and p over q less than 1 over L times Q square. And we would like to investigate the real numbers L, okay? And this is exactly the definition of the Lagrange spectrum and the Lagrange number. So if you take alpha is a real, then you compute L alpha is a sub over all L that satisfy exactly alpha minus p over q in absolute value less than 1 over L q square. And then you define the Lagrange number, Lagrange spectrum when you take alpha is irrational. And for the problem here, we just have a look to the Lagrange spectrum below 3 in order to have a very particular property. And we will see sequences and so on. Okay, let's try. So the first L, in fact, is a square root of 5. This is a theorem of Hurwitz. And if you take an irrational, there are infinitely many rational numbers p over q such that the distance is less than 1 over square root of 5 q square. So it means that, in fact, if you compute the alpha with this property, you find that the alpha is exactly 1 plus square root of 5 over 2. So L of the number, golden number is exactly square root of 5, okay? So this means that the golden number is the most badly approximated quadratic number, and square root of 5 is the first element of the Lagrange spectrum. So this is exactly the first L on your Lagrange spectrum. So we can go further. Okay, so we remove, in fact, all the cousins of the golden ratio. It means that you are using a homography transformation like this. If you take alpha, all the cousins of alpha are beta, such that beta equal to A alpha plus B over C alpha plus D. So this is exactly a homography transformation. And we have also that AD minus BC equal plus or minus 1. So in fact, all alpha and beta, all cousins, are the same Lagrange number. So we have L alpha equal L beta. This is why we remove all the cousins. And if you remove the golden ratio and all the cousins, then the next value is a square root of 8. and it is associated to 1 plus square root of 2. Okay, so this is the second badly approximated quadratic number. And then the next, the third value of the Lagrange spectrum is square roots of 221 over 5, and so on. So we can compute the Lagrange spectrum, but it's really, it's really difficult. So we have to make a link with the continued fractions. So here, this is a nice book of Berstel, Love, Reutenauer, and Saliola about combinatorics on words, and you can see this definition of the usual definition of continued fraction representation. And then alpha, you can write it at A0 plus 1 over A1 plus 1 over A2, and so on. And here, this is the values of your continued fractions. So it's for alpha, it's A0, A1, A2, and so on. So the first value, alpha, is associated with 1 plus square root of 5 divided by 2. And if you look at the continued fraction, it's always 1. Okay, it's a sequence of 1. And the second most badly approximated quadratic number is 1 plus square root of 2. It's a sequence of 2 in your continued fraction. And the third one is a sequence of 1, 2, 1, 2. It's a periodic sequence. So we have a really strong link between Lagrange spectrums and combinatorics of continued fractions. Okay, let's go further. So this is a Markov numbers. It's the set of 1, 2, 5, and so on, 13, 29, 34, and so on. And you can have all the values of your Lagrange spectrum by replacing the m, by taking 1m of your Markov numbers, and you compute the square root of 9 m squared minus 4 divided by m. And this is exactly the value of your in the Lagrange spectrum. And in fact, we can have this nice representation by a tree. So let's define carefully Markov numbers by using a tree, in fact. So, it's a theorem, in fact, but you can define the Markov numbers here. The Markov numbers are the solutions of the following Diophantine equation: x squared plus y squared plus z squared equals 3 x, y, z. And you have x, y, z are positive integers. Okay, let's have a look. So the first triplet, the first solution is 1, 1, 1, because 1 plus 1 plus 1 equals 3. Oh, good. The second triplet is 1, 1, 2, because 1 plus 1 plus 4 equal 6. Okay. And now we have a triplet with all values, distinct values. It's 1, 2, 5. So this is the first triplet with all distinct values. And you can compute that 1 plus 4 plus 25 equal 30. And here we put the maximal value of your triplet in the middle, okay? So you have, for example, 5 in the middle, and then you have a left value, which is 1, and the right value, which is 2. And this gives birth to 2 new solutions of your Diophantine equation. For example, if you fix L and the middle and M, then you add a new value which is 3L M minus R, or you fix the middle and the right value, and you put in the middle the new value, which is 3mr minus l. And then you can compute all triplets like this. So we have this rule, and we have the infinite tree. So here you can see the first triplet degenerated triplets. And this is your tree roots in the triplets 1, 5, 2. And here also, in each position, you have a binary tree. So you can add 2 new values and so on and construct your tree. And this is a real nice tree. And you have all values on your tree are Markov numbers. And in particular, this is a Frobenius conjecture. So each Markov number is a maximum of a unique Markov triple in the Markov tree. So here 5 appears in the middle here, and okay, 29 appears in the middle here, and okay. So the conjecture is really easy to state. You just have to look at all triplets in your Markov tree and try to prove that the maximum of a unique Markov triple is on each triple. Okay. So we can see that here we can find nice values, 5, 13, 35, 34, and so on, 89. And this is not so far from the Fibonacci numbers. In fact, you are taking Fibonacci numbers like this 5, 30, and so on. You take Fibonacci numbers with position 2n plus 1 in your sequence of Fibonacci numbers. And this is Markov values, which are Fibonacci. And if you look at this is the left branch. If you look at the right branch, you can see that we are able to use Pell numbers with recurrence like this, Pn plus 1 equal 2Pn plus Pn minus 1. And here also we are looking at Pell numbers in position 2n plus 1. So you have 5, 29, 169, and so on. So, okay, we are able to find 2 branches, and it is not easy to prove that the set of Fibonacci with rank 2n plus 1 and Pell numbers with rank 2n plus 1 are distinct except for this value 5. And you can see the paper of Vuillon, Reutenauer, and Sixek. And it's really nice to see this paper, but it's really technical and difficult. So maybe linear recurrences is not the best tool to investigate the problem, but it's interesting. So this is why we look at this problem with a combinatorics of words point of view. So we take a word W. So we have later W1, W2, Wn on a finite alphabet. Here the finite alphabet will be AB, a binary alphabet. And we define, as usual, so the set of all finite words, which is a sigma star. And for example, AABB is a word on this alphabet, AB. We are able to define the prefix. So this is the beginning of a word. We define the reversal of the word. You read by a tilde, W tilde. You read the word in the other direction. So it's WN, WN minus 1 to W1. And of course, a word is a palindrome if it is equal to its reversal. So W equal W tilde. For example, ABA is a palindrome, and AB is the prefix of this palindrome. Okay, so now we can define the palindromic closure. It's a very nice tool introduced by De Luca. So the palindromic closure of a word X on the alphabet, binary alphabet AB, is the shortest palindrome having X as a prefix. It exists and is unique. And it is denoted by X plus. Oh, for example, if you take X equal A, so A is already a palindrome. So X plus is A. Okay. So if X equal AB, then you take in the middle of this B, the center of symmetry. So you have ABA, which is a shortest palindrome with AB as prefix. So this is X plus. And in general, to compute X plus, you have to look at X prime Y, with Y is the longest palindrome suffix of X. So the palindrome is, the suffix is the end of your word, okay? So you can see B is a, for example, here is a longest palindrome suffix of AB. So this is the center of symmetry. And this is why we take X prime and we reverse X prime. We compute X prime tilde. Okay, this is a way of finding the palindromic closure. So let's try. With a more difficult example, now we would like to iterate these processes. So this is iterated palindromic closure, also defined by De Luca. So you have a directive word. So D is a directive word. Is a word D1, D2, and Dn with n letters. And pal of D is just pal of D1, D2, Dn. And it is recursively defined like this. You compute pal of D1, D2, Dn minus 1. And you add the letter Dn, and you compute the plus operator. Okay, and we have pal of the empty word is the empty word. Okay, let's try to compute pal of ABA. So this is a directed word, ABA. And we will see that the pal of ABA is ABAABA. Okay, let's start. So pal of the prefix here of your directed word, pal of A is A. Okay, good. So now here we have to compute pal of ABA, we have to compute pal of AB and pal of A. Oh, we are able to compute pal of A. So let's try to compute pal of AB. It's pal of A, and I put the last letter of the directed word, so it's a B. So pal of A is A, so I have to compute AB plus, and the palindromic closure of AB, we have already seen that it is ABA. Okay, so now to compute pal of ABA, you compute pal of AB, you put the last letter here, so it's a A. Pal of AB is ABA, so we have to compute ABAA plus. And the center of symmetry is between these two A's here. So you reverse AB at the end, so it's ABAABA. So another way of computing this directly, just by looking at the words that you are taking. So for example, you are taken. So here the directed word is ABA. So let's start. First of all, I have to compute the palindromic closure of A. So it's A. Then I add a B. This is the B is the second letter of your directed word. And then here you compute the palindromic closure. So it's ABA. And now we put the last letter of your directed word. This is the A, and you compute the palindromic closure. So it's ABAABA. So this is a way of looking at the directed, iterated palindromic closure by looking iteratively, putting each letter of the directed word. Okay. And this is a theorem with Christophe Reutenauer. In fact, we use this palindromic closure and also the two-Morse substitution, which is theta here with this is a two-Morse substitution that maps the letter A to AB and the letter B to BA, as usual. And in fact, in order to have Markov numbers, we compute PAL of theta of PAL of AV. AV is just a words on the alphabet AB beginning by A. Okay. And you put the length of this word, you add 2, and this is exactly a Markov number, distinct from the degenerated cases, distinct from 1 and 2. And what is really nice, the mapping is from AB star to the set of Markov numbers. And the mapping is surjective, except for the value to 1 and 2. And if you are able to prove the injectivity of this mapping, then you have the Frobenius conjecture. It means that this word here, you take the length of this word, and you just have to prove that each word are with distinct 2 by 2 distinct lengths. Okay, let's try to compute the first Markov number, which is 5. Okay, so we take V here, which is the empty word. So we just have to compute PAL theta PAL of A. But PAL of A is A. So now we have to compute theta PAL of A. So A goes to AB. So this is AB. And now we have to compute PAL of AB. And we have seen that PAL of AB is ABA. So this is a word of length 3. If we add 2, we have the first Markov number, which is 5, and so on. For example, if we want to compute 13, we take V equal A. So we have to compute PAL theta PAL of AA. PAL of AA is a palindrome, so it's AA. So theta PAL of AA is ABAB. And so now we have to compute PAL of ABAB. So A, we take the first letter A, it's a palindrome. Then you put a B, compute the palindromic closure, it's ABA. And you put the third letter, it's a A. The center of symmetry is between these two A's. So it's ABAABA. You take the last letter, it's a B. So now the center of symmetry is between BAB, and you reverse. Okay. So it's a word of length 11, and if you take you add 2, you have exactly your Markov number, and so on. So if you look at the 29, which is a PAL number, we just have to take V equal B and compute pal of theta pal of AB. Pal of AB is ABA. If we take theta pal of ABA, so it's, no, excuse me, it's theta of ABA. It's AB, BA, AB. And then we have to compute pal of this word. So now we have to be careful. We put A, then a B, and compute ABA as the second palindrome, then a B. We have a third palindrome here, AB, ABA, and so on. So we are able to compute where this A, this other A here, and the last B here. So we have a word of length 27 plus 2 equal 29. So great. In fact, we are constructing here, these words in the middle are in fact the middle of Christopher words. There are also central words in the vocabulary of Berstel and De Luca. And this is why we have a word of length something, 27, for example, and we add 2 because in order to compute the length of the Christopher word, we must put at the beginning A and at the end a B. And here you have a palindrome. So this is why in the formulation of the theorem, we have the length of pal, theta pal of AV, and we add plus 2 because we add these 2 letters in the Christopher words. Okay, and we have many information in the Christopher word. We can define it with with discrete geometry, or you can define it also with a Cayley graph and a generator if you want, if you prefer. So with discrete geometry is interesting because we have to look at numbers like this, IB minus G A over A. So for example, here, if you look at the Christopher word, path of the slope 4/7. So you have A equal 7 and B equal 4. And then you compute your value divided by 7, and you compute 0 plus the generator, which is B. So, and then plus B equal 8/7, and so on. You can define the computation, and you are computing modulo, in fact, A plus B. And this is exactly the definition here. You are computing a word using a Cayley graph, and you are on the Z over 7 plus 4 Z. So it's really interesting. We have a lot of structures. And you have a direct link between Christopher words and continuous fractions, because here, if you are looking at a Christopher path from 0, 0 to 2310, then you have a continuous fraction associated with the 10/23. And if you compute the continuance, so it's if you take the beginning of your sums, then you have 1/2, 3/7, 10/23. And this is exactly the Christopher path, which are, and we extend the Christopher path like this. So it's really interesting. So now we have a lot of information and we want to go further. In fact, it's not easy to compute directly the length of your word. Here you have a word of, you add the first palindrome is of length 1, then 3, then 5, then and so on. And if you want, you can try to look at the length of the words that you are adding to the previous construction. So here you have a, then you add BA. So the length here it's 1, then 2, here it's 2, here the length is 5, 5, and here the length is 12. Okay. And there is a strong link between this length of the adding part of the word and your computation. Oh, let's try. Now we look at the directed sequence. It's just theta pal of AV. And then we would like to compute the length of pal theta of pal AV directly by looking at the length of the words. We don't want to construct the words, but just the length. Okay, so let's try. In fact, we have this nice recursive formulation. So your Markov numbers will be the sum of the LG here, from G equals 0 to the length of your directed word. So the directed word is D1, D2, DD, length of the directed word. So if you want to compute LG from the previous value, either DG equal DG minus 1. If in the directed word you have exactly the same value, the same letter, so the value LG is equal to LG minus 1. Okay. Now, if in your directed word, at position G, you have a letter distinct than the letter in position G minus 1 in your directed word, and distinct from the letter in position G minus 2. So maybe it's A, B, A, or B, A, B, okay? Then you compute the LG is the sum of the two previous values. And if you have DG distinct from DG minus 1, and DG minus 1 is equal to DG minus 2, then you make the computation of the third last values. So either your transformation is like Fibonacci, or your transformation is like Fibonacci. And then you can compute directly your Markov numbers. So it's interesting. For example, here, if you want to compute the Markov numbers associated with theta pal of A, so V is the empty word. So this is why V, here I put the empty word. So you have to compute, you have to use AB as a directed word. And for simplicity, you can put directly the values. This is in position 0, in position 1, in position 2 on your directed word. And if you compute the sum plus 1, this is exactly your Markov number. And you can find it, for example, for V equal A. So now you are looking at theta of pal AA. So the directed word is AB, AB. So here you use exactly the same computation at the beginning. You have a 1 in position 0, a 1 in position 1, a 1 in position 2. And as the three letters are distinct, or as you have this letter distinct like this, you have A, B, A, you use the second rule. So you make the sum of the two last values, so it's a 3. Here you have a BAB, so you use the second rule also, and you make the computation. Okay, so here it's only Fibonacci rules. So this is why you find Fibonacci number. And in fact, this is general. If you look at the directed words with A and with A power K value letters, then this is a Markov number, which is a Fibonacci number. Okay. So now if you want to construct Pell numbers, you have to look at something like that. So you have to take V equal B and compute theta pal of AB. So it's theta of ABA and so on. So here it's much more complicated. So at the beginning, you have a 1 position 0, 1 position 1, a 2 in position 2. As here at the end, we have B, B, A, we use the third rule here. So the computation, no, sorry, excuse me. So here, as we have the same letter, B and B, we use the first rule. So we take the value here and copy here. So it's a 2. So now we are looking at this position. We have A and BB. So A distinct from B equal to B. So we use the third rule, and then we add the last third values. So it's 5, 2 plus 2 plus 1, and so on. Here you have the same letter in the directed word. So you take this 5, you put here. So now in this position, you have a B, and this is distinct from A, and A is equal to A. So you use the third rule. So you have 5, 5 plus 2. So it's 12, and so on. So in fact, the directed words with A, B to the power K are the directed words associated with Pell numbers, Markov numbers that are Pell numbers. And if you want to have a mix of this, then this is an example. For example, here I look at theta pal of A, A, B. So you have the A, it's a palindrome, you put a B, and so pal of AAB is AAB, AA. So you put theta. Theta is just, you have a AB or BA. So you have a block of AB or BA by using exactly your directed word. And then you make your computation. You can see that here you can use Fibonacci rules. And then you have repeated letters like this. Then you use Fibonacci rules, but Fibonacci rules, you use Fibonacci, and here you have the same letter. So in fact, so you copy the value. So this is why here you have Pell rules, in fact. So you alternate between Fibonacci rules and Pell rules in order to compute these values. So we are at the end of the talk. We have now new combinatorics of words tools in order to investigate Markov numbers. We have a lot of structures because here pal of something is the center part of the Christophe word, and we can use discrete geometry in order to try to understand the structure of a word pal theta pal of AV. And this is why it's interesting. Maybe we have all combinatorics on words tools in order to tackle this conjecture. So this is a conclusion, how to prove that the words pal, theta, pal of AV have 2 by 2 distinct lengths. What are the properties of the LEs? Because it's really a crucial, if you investigate the growth, the way of adding words and the growth of your function, you can maybe investigate the Markov numbers and how to use now discrete geometry and Christopher Reutenauer in order to prove the Frobenius conjecture. Okay, thank you very much. If you have some questions.